This is our research and development area back here, and we're crammed. But you can see the gist of it here. You've got a power unit over on the ground there. It's full of oil. You've got the valve, which I showed you earlier. Just above that, you have the main control box. And that control box basically says yes, no to those valves. Pumps oil through a hose into this black cylinder here. Cylinder then fills with oil, pushes up that seal piston, which is on a wheel, rotates the wheel. The rope moves at a 2-to-1 ratio, meaning that for every 1 inch that wheel travels, this car will move 2 inches. The car is held on a metal frame. You can see it here. It's on guide rollers. The guide rollers are hung in a cantilever position just by force, and they ride up and down this 8-pound per foot T-rail. The T-rails are held onto the wall with rail brackets at a predetermined height, and all this is an engineering feat because there's a lot of complexities to the math to make sure that you don't run out of room or hit the top floor or anything like that. Where the MCU comes into place, this is mimicking a lot of the stuff on the top of the car. So this is our MCU chip here. And as we're going to move into the electrical area, I'm going to have Sean Moffat, our electrical manager, give you a breakdown of what the difference is between allowing us to use this chip with the programming languages that you guys learned versus our previous version, which was complete relay logic and much more robust, as you'll see. So that sits on the car top. That you're familiar with, that's the COP, car operating panel, you'd see in an elevator car. Here's your various interlocks at your floor levels, your call stations that you would find in the hallway, and this is just an emergency stop, as is this. So this allows us to sort of play with the product, add new programming. We have a digital readout for feedback, and this gives Mike Bruner, who is our research and development person who Ignash has worked with, this gives him his lab space to actually coordinate and do studies and test runs and troubleshooting and everything. This is where all that happens. Okay, so now I'm going to break and we're going to go up and see the electrical department where Sean Moffat's going to give you a breakdown of an old system that we have on the table versus the new system that we've done with the MCU chip. Okay, now we have Sean Moffat, manager of the electrical department, and he's going to briefly break down 2 electrical systems. We do have one on the table that we're using an older relay logic switch style system, and then we have one next to it where we're implementing the new Bruner electrical system that utilizes the MCU chip. So Sean, if you could give us a breakdown of what we're looking at, please.
So this is the switch system. We've laid everything out on the table. Just to quickly, both systems have a car top with the board with everything that's on the top of the car, and then travel cable down to a main controller. The difference is being the positioning system that's used. So in this case it's switches. So we'll have 2 switches on struts in the hoistway with cams that hit them as the cab moves. Bottom floor, 2 switches at the top floor, an extra switch for the final limit. Middle floors require a minimum of 4 more switches each floor. So a 4 or 5 or 6 top elevator has a lot of switches in the 20 range. What's common, of course, is the interlocks, call stations, and all that stays the same. But the switching, and of course the way the information is processed, in this case the switches activate relays which then allow the power to go or allow calls to be placed, etc.
And is it safe to say then for every one of those switches, which there are so many, you've got to run a wire back and terminate every single one of those wires in the junction boxes, which is all time consuming from a production standpoint?
The connections are a lot more vital and a lot more complicated because the connections depend on how it works. So we end up with large junction boxes with time-consuming connections, upwards of 50, 60 connections for even a simple elevator.
Like this is only a 2-stop, and we can see how many connections are necessary.
The other thing I've thought of is that the wiring of the elevators completely changes depending on the number of stops, the types of doors. So there's a separate set of wiring diagrams required for a 2-stop, a 3-stop, a 4-stop, a 5-stop, automatic doors, manual doors. there was over, when we were making these continually, like regular production, there was over 25 different sets of plans to make 25 versions of the elevator.
Wow. Okay. Okay, are we ready to transversely show?
Our main spot was a nice place, but you get people walking in.
Okay.
So here we have a car top again, although we've added a main circuit board with a microprocessor, or in this case. We have a main controller still, which connects the power to the pump and has some of the main relays. And we still have call stations and interlocks on the floor with local junction boxes in the hoistway and just a single cable going back. But the positioning system now, all those switches up to, like, say 20 some odd switches, is replaced by 3 optical sensors. Three optical sensors which can connect to the microcontroller. So the microcontroller is going to interpret the data that it gets from these to determine the position of the elevator at any time, and then decide where to go next and what relays to turn on. Also, we have all the dip switches here, which allow us to configure this board to be either a 2-stop straightforward Elmira or a 5-6 stop Cambrian with 2 or 3 doors in the cab that open on different floors. One big advantage now, of course, is the wiring diagrams. There's only one set of wiring diagrams for any number of stops, any combination of automatic manual doors. It's a very versatile board. You can also select special features now with the microcontroller, like automatically homing, like automatically going to the top floor when not in use. Other things which obviously were not very easily done with a switch-based, relay-based system. Timers, all the timing functions, of course, are all taken care of here. Whereas over there, if you wanted to automatically turn the lights off, that was a $35 timer. In this case, the board does all that as well, so it adds to the cost effectiveness.
How long would it roughly take to make the old switch system on an average 3-stop inline elevator?
The old switch system, if the controller and a few things were ready, it was easily over 8 hours, probably about 9 for a 3-stop.
What comparatively would you say for this system with the same amount of prep work?
With the same amount of prep work, we're looking in the neighborhood of 4 to 5 hours for a 3-stop.
So we've saved about 4 or 5 hours of labor time.
We've cut the labor in half. Also, the labor has become a lot less, it's a lot harder to make a mistake, let's say, on this system with one drawing, but from elevator to elevator, it's very consistent. Mm-hmm. So it's hard, the people get more used to it and there's not as many mistakes. With the other system, there was such a drastic difference between a 6-stop, 5-stop and a 2-stop and a Cambrian and Elmira that you never saw the same elevator twice in a week.
So your margin of error goes up with every one.
There was a lot more connections and everything changed. It was different on every job, so it led to more mistakes.
Perfect. Okay, well, thank you very much, Sean. I guess hopefully that does it to give you guys a little slight, just in a real snapshot. You can see car operating panel, nice clean car top, one piece of travel cable that goes up and down with the car, a controller, and some locks. You have the exact same 2-stop elevator with the older system. And even from a real simple perspective, you can see a whole table full of wires, connections, and terminals, which make it more complicated, more time consuming, and increase your chance that you're going to have an issue. So with that, we'll adjourn. Thank you.